Okay, let's get started here. So we will continue in Chapter 3 today. I doubt that we'll actually get to Chapter 4. Project number 3 is due Thursday, October 18th, provided that we get far enough in Chapter 3. And I think we will today. If we don't, I'll let you know. Of course, we will not be having class next Tuesday due to fall break. Are there any questions? Okay, we left off last time on page 339. And what we've been talking about is ways to determine if the variance of t is a function of theta. And the reason that's important is because ideally you would like your variance not to be a function of the parameter that you're trying to estimate. And for a number of reasons. Now, excuse me, ideally what we like to be able to do is judge whether or not the variance is a variance of t is a function of theta by doing a plot like this that we had drawn out. So let me do some erasing here. And on the left side, we see an example where the variance is not a function of theta, generally speaking. And on the right side, we see an example where the variance is a function of theta, generally speaking. Now, of course, we won't know what theta is. And if you're in a completely non-parametric setting, you will not necessarily have a nice functional form for your variance. So what can we do then to make a determination if your variance is a function of theta? And that's where the bootstrap comes in. And so we looked at how we could, let's say, maybe plot t star on the x-axis and v star, some estimate of the variance calculated on your resamples, on the y-axis. And do the same kind of judgment about whether or not the variance is a function of the parameter of interest. Of course, then the question comes down to what to use then for this variance that you're putting on the y-axis. And we looked at a number of different possibilities that we could do. So, for example, today we are going to look at using the non-parametric delta method. And we can also then actually have a bootstrap estimate of the variance there too. But since this is a bootstrap estimate, you're already taking resamples in the first place, this means that you're going to have to actually implement a double bootstrap. Okay. So that takes us to where we left off. This is example 3.21 in the book, dealing with a correlation coefficient, very old Pearson correlation. Let's let rho be the true correlation, and r be the correlation coefficient. And again, this is one of the times in the course where the notation can be a little difficult because we use the letter r for a number of different things. So please be careful about that. So the purpose here is to show that the variance for R itself, the Pearson correlation coefficient calculated on the sample, is a function of rho, the true Pearson correlation coefficient. That's the purpose. And then to show how if one would do a regular old variance stabilizing transformation, then that's commonly used. You've all seen it before, even if you've never taken an asymptotics course and actually tried it before. But this variance stabilizing transformation then causes then the transform statistic to no longer be a function of rho. Okay. Let's first talk about this variance stabilizing transformation to see how it comes about. I'm not going to go through all the details, but just to give you a general idea, I think it's important for you to see, especially hopefully you will see something like this in other classes. If you want an actual book reference where it's actually derived, you can look at Lehman or Ferguson's book. And what one can show, this is typically done in an asymptotics course, is that the square root of n times r minus rho converges the distribution to a normal random variable with mean 0 and variance 1 minus rho squared, that whole quantity squared. So the important part here So there's our parameter, and look at what's happening here. It's in the variance. Just to give you a little background, how does one actually prove this? Actually, it's just a combination of the central limit theorem and also using what's called the multivariate delta method. Okay. Now, one can show that the variance stabilizing transformation, and we'll briefly talk about how to do that shortly, is this. H of rho is equal to 1/2 times the log of 1 plus rho over 1 minus rho. Is this a transformation all look familiar to you? Maybe some of you have seen it before. What's it called? What's a special name? It's named after a person. Yeah, just say Fisher to anything that's named after a person in statistics, and often you have a good chance of getting it. Yeah, this is called Fisher's transformation. And this is used to derive the most often used confidence interval for a correlation coefficient that maybe you see, for example, often, at least I talk about it in this class in the multivariate methods course, our stat, the numbers escape me, is it 730? 873? It was 730 at KC. It's interesting that often the first schools that you go to, especially in grad school, when you just talk about numbers for courses all the time, and then when you go to another grad school, and then when you go to another school as well, the number that always sticks in your head is the one that you had first. So my course numbers at K-State still stick in my head as the corresponding courses here at UNL, and every once in a while I'll throw out the wrong number. Anyway, so one could show then that if we work with this transformation, look what we get. A standard normal random variable, asymptotic. So that's good. And I think if I bring up one point now here, this will be helpful later. What is the asymptotic variance for R here? Just talking about R. Is it this? No. What else do I need? Not square root of n.
Over n.
Also, what's then the asymptotic variance for h of r here? One over n. Okay, notice how that's constant. So the reason why I bring this up is often, especially for students who have not done an asymptotics course, you often forget this little part here. Because this is, in the end, often you want to just get that asymptotic variance. And how would you get it? Well, you need the n part. How would you, if I were to put a hat on here, what would you do? Replace this with R. Okay? It's just a common thing that students sometimes forget. That's why I wanted to bring that up. Okay. So where does this transformation come about? It's an application of stuff that I first showed you in section 2.5, I believe, where what we need to do is take the integral of 1 over the square root of the original variance for your statistic of interest. In this particular case, the variance is, again, 1 minus rho squared, that whole quantity squared, and I take the square root of it, so that's why I just have 1 minus rho squared. Okay. So, I can do some factoring. I can also use partial fractions as well. Hopefully all of you remember that from Calc 2. And do the integral and stuff, and this is just how you get the transformation. Now, let's put some data with this. Our authors say that 20 observations were taken from a bivariate normal distribution for their example, and then the observed correlation coefficient was 0.74. Unfortunately, they don't ever give their data. It's not in the boot package. It's not on their website. At least I've never been able to find it. So what I decided to do is actually simulate some multivariate normal data. Simulate some bivariate normal data where the true correlation coefficient is 0.74 for lack of knowing what it actually is. So it seems to make sense. So how can I simulate multivariate normal data? All of you have actually done this before the day number 1 quiz. Use the MVT norm package and the RMV norm function. Just to review, sample size of 20. The mean doesn't really matter because I'm working with the correlation, so how about we just pick zeros? My covariance matrix is this. So the variances are 1, covariance is 0.74. What will be the correlation matrix? Same thing, of course. So let's go ahead and simulate the data, and that's what it looks like. Of course, whenever you simulate data, it's good to do little checks. So, I could, let's say, make sure the mean was approximately 0, make sure the correlation matrix is about what we get. And so, for example, or about what we said. So, for example, here's the correlation matrix, and we can see that 0.789 is the sample correlation for this particular data set when I use 0.74 for the true. That's good. Now we can do the bootstrap here, since we have a data set. As always, we're going to need a calc.t function. So calc.t, pass in the data, pass in the indices, and because we're going to use a double bootstrap, I have a default here set of m equal 800. Now note that this data is in data frames, so notice how I set up d gets data, bracket I, comma, and brackets. To make sure I get the row numbers from the data frame, or get specific rows from the data frame. Sample size, I estimate my correlation coefficient using the core function, just like what I did here. But remember, I only need the 1, 2 element to look for the correlation between the two variables. Then, for a double bootstrap, then I implement the boot function. I call a function called calc.t2, which contains the calculation of the Pearson correlation coefficient once again. Now I'm going to calculate 4 different variances here. Okay? These variances are detailed on page 345. If you want to look back and forth between the 2 pages. First of all, I used the non-parametric delta method to calculate V. Now, I'm not going to go over the derivation of that. This is actually in the book. It's equation 240 on page 48. So you can verify on your own that I did actually program it in correctly. But this is the actual formula. Next, later in the book, they have a transformed, they find a variance for a transform statistic, which, how should I say, which comes about through this, this transformation. So note that, for example, to give you some idea, so this goes back to the asymptotic distribution again. If I were to stick in here a 1 minus rho squared quantity squared, obviously then that's how I get my variance of 1. So in other words, and this is where this came about, the derivative that I'm actually sticking in here. Sorry, I know I'm writing over stuff. That derivative is actually equal to that. And what we needed to do was figure out, well, what would be then the function h itself, the non-derivative part, and that's why we ended up taking the integral. Anyway, though, so that's why you see here 1 divided by 1 minus r squared, essentially. Notice the square right here, too. You can look at the book in Chapter 2 where they actually talk about this transformed, the variance of this transform statistic. The hope is that this then is the new variance that we get from a variance stabilizing transformation with respect to the non-parametric delta.
But the transform one, the BL.
I'm sorry, yeah, I put it.
I was like, whoa, that was there. Okay.
Okay, so that's variance number 2. Variance number 3 then comes about through the double bootstrap. So I just simply take the variance of what I get from my boot.res.m. And then lastly, well, how about we work with the transform statistic itself? And note that I don't need to create a new function to calculate this transform statistic. I just have 0.5 times the log of 1 plus boot.res.m $t. So these are like my t stars divided by 1 minus boot.res.m $t again. And again, we would expect that since I'm using this transformation, that the variance will be stable. Look what I return. I return 5 different things, the 4 variances, and you can say t itself. Tried it on my data just to see what I get, and this will match in the original correlation that we had previously. Okay. There's a small error here. This should not have an asterisk there. Okay. So of course, if you wanted to, you could also use like the jackknife or the regression method to get the empirical influence values and use that then to come up with these estimated variances too, if you wanted to. And let's go ahead and implement the bootstrap here. It takes about 1 minute if you're at least running on my computer. And again, because you're using the double bootstrap, you're using 999 resamples and 800, let's say, second level resamples. Here's the output. Here's the results from the plot function. You see that we have a skewed distribution, or R itself. Now, just as a reminder, note that when you say plot boot.res, it goes to the first column, boot.res $t, by default to plot. There is an index argument that you can put in that plot function that allows you to go to a different statistic that you're calculating. Okay, some other little small changes to the notes. Notice here in blue, I've added a subscript R. That would have been better for me to say there. Well, it's up to you if you want to actually do that. If you do that, then you need like a subscript R here as well. The main thing is just to realize what you're calculating for every single reason. That was the point. And perhaps I went overboard then with notation, especially since we have an R subscripted by an R. Oh well. Okay. And at least when I printed it off on page 345, this little part there corresponds to what's circled there. Okay. So we've done all these calculations now. Now what we basically want to do is do some of these plots that we were looking at before. So let's begin. Now I'm going to just basically reproduce some figures that are in the book. So I'm going to plot what would be T star, or equivalently R star, versus VL star. Now, what I'm also going to do is this. Remember what we said was the asymptotic variance for R itself. 1 over n, 1 minus estimate there. 1 minus R squared, that quantity squared. So, what we should be able to do then is do a plot then of the statistic versus the variance, and plot this basically as a line on the plot. And you should be able to see that relationship hold. So that's why for the curve function, I'm using this particular function when I'm plotting. I'm also going to add a smoother to the plot as well. Does everyone remember? Have we talked about smoothers here before? Does everyone know what a smoother is? Can we say what a smoother is? Silence means no. So I'm going to move on. And I'm going to put a little legend on the plot too. And this is what we get. Let me actually blow this up a little bit. And just focus on the left here. So, T star, VL star. The asymptotic variance is plotted in blue. There. And we can see how those red points from the 999 resamples, those red points generally follow that pattern. And in fact, with the smoother there too, that smoother generally follows that pattern as well, indicating that, again, it was an asymptotic variance, remember, we have a sample size of 20. That asymptotic variance seems to follow the true pattern. Now you might be saying, well, wait a second, what's happening out here? Well, what's the problem with smoothers often on the ends? Not going to work very well, so that's why I'm not worried about that over there. So that's kind of cool that we show with the Bootstrap, we are showing how this variance actually follows this pattern. Okay. Now what I do next is I do a second plot where I use the transform statistic. So you can say that on my x-axis here, I'm going to plot T star. And on the y-axis, I'm going to plot this V, what's the notation? It's V star tran L. So the non-parametric delta method applied to the transform statistic, calculated for each resample. And remember, based upon what we discussed before, well, what would be the variance of this transform statistic, the asymptotic variance? 1 over n. Let's plot that. I'm also going to plot a smoother and put a nice little legend on it as well. And that's what's plotted on the right side. So the blue line is the asymptotic variance, because it's just 1 over n for any possible value of that transform statistic. And you can see while it's not in the middle of the points, kind of capturing what's going on. The smoother itself, generally speaking, is kind of horizontal. Again, don't worry about right at the edges. And so it looks like this transformation works. Kind of cool. Note that the mean, let's see now. So the mean of all these variances on the y-axis is probably right about there, 0.054. This is again on page 346. What is the asymptotic variance? 1 over 20, 0.05. Kind of similar. And again, it's an asymptotic variance. We have a fixed sample size here, so I'm not necessarily surprised that it's different. At least a little. You know, what I would expect as n gets bigger, that those two match up more. So it's a really interesting example to do something like this. Are there any questions about it? Some notes here. So the smoother that I use comes from the super smoother function. If you want to know more about that, look at the help or take a look at Venables and Ripple's book. Let's see here. We talked about that. Now let's do this let's do the same thing now with the double bootstrap. So remember, I guess it would be column 3 and column 5 of boot.res $t gives me my bootstrap estimate of the variances. Well, let me just say this. So the first plot that I'm going to do now, again, is T star versus V star boot. And I'm again going to put on that asymptotic variance for just the correlation coefficient itself with the smoother. And I'm going to control the y-axis on each of these plots to be exactly the same, so I can make direct comparisons between when I use the bootstrap, or the double bootstrap I should say, or when I use the non-parametric delta method. So essentially, the plot on the right is exactly what we've seen before, but it just has a bigger y-axis scale. Now, why am I doing this? Well, remember that the bootstrap itself, when we're finding this variance, is not relying on this linear approximation that the non-parametric delta method is. Okay? And this is what we get. So what's happening here with the bootstrap? The double bootstrap. In comparison to what the linear approximation, the non-parametric delta method gave us. It's saying the variance is actually bigger. We don't actually know if it's more or less.
Compared to the asymptotic.
Yeah. So I mean, you can see that. I mean, the blue line's drawn exactly the same point on both the plots. You can see how the smoother says, okay, your variance actually should be a little bit higher. To be honest, I probably would trust the bootstrap, the double bootstrap here more than the asymptotic. So again, it's 20. That's, again, interesting. Well, what if we now also try this transformation as well? So, again, what I'm going to do is plot h of t star versus, now this is v star tran boot. And that's going to be on the left. On the right side, it's going to be exactly the same plot that we saw before with the non-parametric delta method. And I just put everything on the same y-axis scale to enable our comparisons. And again, what you see with the bootstrap, with this transform statistic, it's saying, okay, your variance, I think, is a little bit higher than with the asymptotic or what the non-parametric delta method is giving you. This is the asymptotic variance for both. You can see with your smoother what happens up here. It's actually saying, okay, your variance is a little bit higher, but notice how it's pretty flat. Again, saying that you picked the right transformation. Now, where's one place that we're going to use this transformation later on? We're going to use this in Chapter 5 when we do confidence intervals. This will enable confidence intervals to be better in terms of the true confidence levels. And if you remember the boot.ci function from Chapter 2, there's going to be a particular way that you can specify your transformation, its derivative, and there's one other component you have to specify too, but I don't remember off the top of my head. And it will automatically then use those transformations to then convert back to the original scale that you're interested in. Like in this case, you're interested in what R is, not what H bar is. You're interested in what R is. Okay. Also, just as a note, it's a good time to put it. Chapter 5, practical number 1 in the book, actually contains a nice little example doing some confidence intervals with a correlation coefficient with and without the transformation. Okay, are there any questions? Let's move on then. Page 353. Bootstrap Diagnostics. So, if you remember from like taking a course like Stat 870, or even Stat 875, or any time that you fit a regression model, and there's often some various diagnostics that you can use to make sure that the assumptions that you have for your model are actually satisfied. Also, it helps you detect maybe particular outliers, meaning particular observations that are not fit well by the model, or maybe actually influence the model itself. Well, with the Bootstrap as well, we have some diagnostic procedures that we can do. We are going to talk about one in particular called the jackknife after Bootstrap. And as maybe you can imagine from the name, jackknife after Bootstrap, what you're interested in doing is using the jackknife to see that if I remove one observation from my data set, is my Bootstrap going to give me a whole bunch of different results? Obviously, if you only remove one observation, you would hope that you get similar results. But if you don't, then you might be worried about maybe something's going on with the data that you're not necessarily accounting for. We're just going to talk about the non-parametric case here. The book talks a little bit about parametric. I don't think it's really worthwhile. So again, what we're interested in seeing is what happens if you remove one observation. Let's call it y sub j. What happens then to your resamples? What happens to your statistic itself that you're calculating for every resample? Actually, it's not too difficult to work to deal with. You don't need to, let's say, go take a whole bunch of new resamples where y sub j is actually removed from your data set. Instead, just focus on the resamples that do not have y sub j in it. And that will tell you what would happen. What would happen to your statistic if y sub j wasn't in your data set. So in particular, we can look at the bias of the statistic. So the Bootstrap bias estimate without y sub j in the data set, this is the book's notation, it's denoted like this. B sub negative j is equal to 1 over, this r sub negative j means the number of resamples without observation j in it. Okay? We take that times in the sum of all your t stars where y sub j was not in that corresponding resample. And we subtract off then what is your original statistic value if y sub j wasn't in the data set. So it kind of makes sense. It's just essentially what we have been using for B before, but now without y sub j in the data. So again, here's what we actually had done way back first in Chapter 2 and also on Tuesday. This is the regular old Bootstrap estimate of bias. So you might be wondering, well, how much has the bias changed? Well, just simply subtract the two. And you can make that determination. Obviously, if in absolute value this change is large, then you might be worried. If the change is not large in absolute value, then you're probably not worried. Now, in the book, first of all, they do a few things that are odd. They use capital B's instead of lowercase b's. I like to use lowercase b's here because I'm talking about the actual observed value. But they also say, well, we can multiply it by n. I guess because you have a sample size of n. Okay? And then say the scaling factor n in equation 3.41, which is equivalently this, is not essential. So I say, if it's not essential, why are you even putting it there in the first place? So I'm not going to put it there. So what can we do then because we're going to be calculating this b sub negative j for all observations in your data set. And if you have a large data set, you can have a lot of b sub negative j's. Similar to like a Stat 870 course or 875 course. When you're calculating a lot of different diagnostic measures, what you do is you plot them to get a better general sense of what's going on versus necessarily looking at every single value. So what kind of plots could you do? Well, you can plot this b sub negative j minus b versus the empirical influence values. Why would you want to do that? What does the influence function do? I mean, we haven't, it wasn't necessarily the main point of this class, but in a non-parametric, PhD non-parametric delta, a PhD non-parametrics class, what would they be looking at the influence function for?
So to also measure the influence of that particular observation.
On the statistic, yeah. Okay? So that's why. Now, what we will actually focus on more is this. Plot the quantiles of t star negative j. So in other words, your bootstrap estimate of t without the jth observation minus estimate of t without the jth observation versus the empirical influence values. Plot the quantiles. And also plot the quantiles of t star minus t. So now if the quantiles are about the same, what do you think that says? That the bootstrap is not necessarily affected by this y sub j observation. If, however, the quantiles are different, then that says, okay, maybe something's going on here. Might want to be cautious. Again, it doesn't necessarily mean that there's a problem. It just means that you should maybe be careful and understand the consequences of having this y sub j observation in the data set. Well, fortunately, there's a nice little function that comes in the boot package called jack.after.boot that does this for us. It actually constructs one of the most complicated plots that you will see in statistics. But once you understand it, it can be a useful plot. Note that in addition to the empirical influence values, of course, you can use estimates of them as well. And in fact, that's what jack.after.boot does. Okay. So to look at an example, we're going to look at an example here, try to reproduce the stuff that's in the book. This example 3.24. Frets heads data. This is a classic data set. And what we have here is the head breadth and length of the first two adult sons in n equal 25 families. And when I was reading this example today, I was saying, geez, this is the first time I've been able to do this example where I can say, I also have two sons, and they're not adults yet, but once they become adults, I can add them to the data set. So the data actually comes in the boot package. It's called Frets. And this is what we have here. Actually, I'll show it to you. So we have four variables. L1 is the length for son 1, B is the breadth for son 1, L2 is the length for son 2, B2 is the breadth for son 2. And this is measured in millimeters. Okay. Now, what the authors want to do here is they want to calculate a partial correlation. How many of you have not seen a partial correlation? So everyone's seen it. A few of you have not seen it.
I'm going to admit that I'm pretty sure I have it, but I don't know for sure.
Can someone tell? I guess I have the answer for this. I'm not going to ask you who could tell me what a partial correlation is. But basically what it is, just think of, even if you haven't heard of it, just think of it as a regular old correlation. But it's a correlation between two variables. But taking into account all the other variables that might be in your data set. So in particular, and I don't know why they chose this, but this is what the authors did. They are interested in the partial correlation between B1 and L2 given L1 and B2, or taking into account the effects of L1 and B2. Now again, even if you haven't seen a partial correlation before, I would imagine that all of you have seen it in like a Stat 870 kind of setting, or something very similar. If you remember partial residual plots, remember partial? Does anyone not remember a partial residual plot? Okay. What a partial residual plot allows you to determine is, I might as well talk about this here, so I'm about to talk about this in my Stat 870 class, is let's say that you have your residual here, and you have, let's say, x1 here. Okay. Now, if I had a simple linear regression model, you know, what would this plot be useful for? What's that?
Outliers?
Not outliers. I guess you could for outliers, but that's not what it is. To determine the proper form of x1 in the model. So for example, if you had like a quadratic trend of points, then it's okay, well, maybe a quadratic transformation is needed. Now what a partial regression plot does is says, okay, let's find this this residual, but for, in let's say your response variable is y, I'm using the notation I use in my 870 course. Given, let's just make this easy, we only have x2 also to consider. So let's look at the residual for y, where I've already accounted for x2. Now how is that typically done? And typically we also put x1 given x2 here. How is that typically done? Two different regression models are found. Find a regression model that uses y as the response, x2 as the predictor variable, get the residual. Then do another regression model where x1 is the response and x2 is the predictor variable, get the residual, and that's basically what's plotted here. If you see trends in that plot, that tells you what form should x1 be in the model. So essentially what you're doing is you're removing the effect of x2 from both y and x1 to allow you to see, well, what if x2 was in the model, what kind of relationship do I have left over for x1? Anyway, so you can kind of see how that idea, perhaps I went into too much, that idea is kind of represented by a partial correlation. Given you're taking into account L1 and B2, what's the relationship between B1 and L2? Simply put. Perhaps not simply, but that's what it is. Anyway, so partial correlations are often taught in a course like Stat 870, our multivariate methods course, 873, and sometimes in a linear models course. I had my linear models in multivariate course when I was a student. And this is how you calculate what's called a first partial correlation. So let's say that we just simply have variables x1, x2, and x3. We want to know the relationship between x1 and x2 after you account for x3. And this is what it looks like without getting into the details of why this is the formula. Okay? So R sub x1, x2 is the regular old Pearson correlation between x1 and x2. A second order partial correlation says, well, let's suppose that we also have a variable x4. And I want to look at the relationship between x1 and x2 given x3 and x4. That's how you account. Okay. you want to know more about it, here are some references. Okay. So, back to what we were really interested in. So we need to calculate a partial correlation. And there's a package in R called core p-core, core partial correlation. And it has a function called core to p-core, meaning transform a correlation matrix to partial correlations. And that will do the calculations that we need. You will need to download this package to install more because it doesn't automatically remove it. Okay. So let's look at some stuff here. Let's go over here to 10. So here's my correlation matrix, and they work with the log data too, so that's why you see me using log of frets there. So you can see that there's a high, just regular correlation between L1 and B1, and also there's high correlation throughout. So that's just the regular old Pearson correlation matrix. Then to transform this to the partial correlations, I use the core 2p core function, and notice there's an argument M for matrix. That's where I put my correlation matrix that I have found over here. And there we go. So this right here, for example, is 0.43. Says given the third and the fourth variable, the correlation between the first and the second variable is 0.43. The one that we're actually interested in, based on what this example looks at, is this 0.13. So given the second and the fourth variable, given the first and the fourth variable, what's the correlation between the second and the third? And I guess also in the notes, if you ever want to know how to do a little scatter plot matrix, there's a variety of different ways in R that you can do that. You can use the pairs function. Okay, so our t is equal to 0.1313. Now let's work with this partial correlation now with respect to the Bootstrap. So I'm going to write my usual calc.t function here. Data I. Remember, data in this particular case is actually a data frame. So d gets data bracket I comma and bracket. Calculate my correlation matrix. Calculate my partial correlations, and then t corresponds to the second row, third column of these partial correlations. I can just try it on my data set just to verify that indeed I get the same answer as what we had previously. Let's use the Bootstrap. Nothing really new here. Note how I use log of frets here again, so I need to use the log data. This is what I get. And notice I get the original value back. And now the jack after boot function. Boot.out is the first argument. Put in the results for the boot function. Index as well. I just did this for emphasis. If you had, let's say, multiple statistics that you're calculating for every resample, you could use that in jack.after.boot. By specifying index equal which column of boot.res $t you want. Here the default is 1, but I just put it there for emphasis. STINF stands for standardized empirical influence values. We don't need to do that, so I put false there. I don't know why they have that there. And then you can put a title on the plot. So this is what we get. Here's the plot. Okay, so can you interpret that plot for me real fast? Huh. You know, when you first look at it, it's like, what? What's going on here? Let me take some time to explain it. Okay. Interesting. Just a little side note. A few years ago at the joint statistical meetings, I gave a presentation on using tablet PCs for statistics education. And actually, I used the description of how to describe this plot as part of my presentation because it's a complicated plot. And using the pen can really explain it a lot better than what you can just simply verbally. Okay, so what we see here at the very bottom are what are very, very similar to, but not quite, the L-Jack values. Okay, I'll show you what they are. Not exactly that, but they're very, very close. And at the bottom of the plot, you see all these little numbers. These correspond to observation numbers. So, for example, L-Jack, spell L-Jack 2 is right here. It has a value of about negative 4 points, maybe 8. L-Jack 18 has a value of about maybe negative 1.3. Now you might be wondering, well, why are these numbers kind of not all in the same line? This is just an example of jittering to avoid overlap of these numbers. That's it. So the relative position with respect to the y-axis is not meaningful at all. Now above each of these points, you see asterisks. Okay? What these represent are the 5th, the 10th, 16th, 50th, 84th, 90th, and 95th percentiles of T star minus T, where you remove the jth observation. So, for example, here, this is the 0.05 quantile of the distribution of T star negative J minus T sub negative J.
Specifically negative 2 in that case, because it's the second observation.
Well, the 0.05 quantile should be about negative 0.3, negative 0.28.
No, I'm saying that particular point that you've pointed
For
to.
the second, yeah. So
the J would actually be 2.
Yeah, the J would be 2.
Okay.
For that particular one. Sorry. I was being very general. Sorry, you probably can't see that one. Does anyone need me to put this up higher? Here, I'll draw it up here too. This didn't happen when I was doing the demonstration. Check this out. This is T star minus 2 minus T minus 2, and this is the 0.95 quantile from that distribution. Now, lastly here, the dashed lines now are for the distribution with all observations. So this is for T star minus T itself, 0.95 quantile. And obviously then, throughout then the whole plot, then that distribution would be exactly the same. And so what we want to do is basically do a comparison here of where those stars lie in comparison to the corresponding dashed lines. So when I remove the second observation, what's happening to the bootstrap distribution? the variability is becoming a lot smaller. So we can see the effect that this second observation has. And let's put this into context then. If my distribution changes, how's that going to affect, for example, confidence intervals or other stuff that we do? Well, it's going to have an effect on it. Let's take a look at another one. Well, let's get a different color here. Oh, let's do orange. Let's see there. What are we going to do? I had one picked out before class. Well, let's just do 11. So we'll look at this here. What happens if observation 11 is removed? Not much changes. And ideally, that's what you would like to have. So again, what this is saying is that with observation number 2, the distribution for these partial correlations is going to change some. No, I guess I didn't do this, but I think it would be interesting. What would happen if, let's say, I did actually do a confidence interval with observation 2 removed, compared to a confidence interval with observation 2 in there? It would be interesting to see. I don't know why I never thought about doing that before, but it would be interesting to see that in a practical sense, that how does this affect? Anyway. So is everyone clear about what this plot's representing? Okay. Let's see here. I just want to make sure I talked about everything that I needed to there. So page 360, I use the non-statistical term that the distribution is getting squished when the second observation is being removed.
It's the same as my gesture.
Yeah. Another way that you can get this plot, again, if you remember that the plot function is generic in R, and so plot.boot is actually implemented when I have a object that has a boot class. There's an argument with plot.boot called jack. If you say jack equal true, you can actually get the jackknife after bootstrap plot and get it on the same plot as then the histogram and also the QQ plot. That can be useful. So when I was first teaching this class, often what I like to do is be able to make sure that I can actually reproduce the results without these nice little functions, and that helps you also, learn and make sure that you know what's actually being done. And when I was first teaching this class in 2006, I was trying to do this, and I was getting quite frustrated because things were not working out exactly like I had expected. And so I had to actually go inside the code for jack.afterboot to find out what's going on, what's actually being plotted. And to be honest, I'm not for sure why the authors of this function do this. And the author of the function is A.J. Canty, who wrote the functions for the Bootstrap, or BMA book to begin with. And this is what's actually on the x-axis. Note that what we would expect, based upon what we saw in Chapter 2, we would expect this. So just to make sure you understand what's being plotted here. So this is the average of all your T stars with the jth observation removed. This, again, is the average of all your T stars with the ith observation removed. But let's sum them up over all your data sets. So for every single observation, you're going to calculate a t star bar negative I, and then average over those. I guess to some respect, I would expect this maybe to be close to there. And I would expect this maybe to be close to there. But that's what's happening. And so you can actually get these values on the x-axis out of using the jack.afterBoot function. And this is what they look like. You can compare them to if we were to use the EMP and IM function. And put this on the same screen. And you can see how they are close. Not exactly the same, but they are close. I think, as maybe some of you have found for doing various things for this class, it gets frustrating when you get things that are close and you wonder, is it still right, or is there something actually else being calculated there? And this is the case for something how else it's actually being calculated there. Okay. Next. Actually, let me just briefly mention. Bring that out. Sorry. Let me find the correct file here. So this is project number 3. You don't need to get out, so I'm just going to mention it just very shortly. So problem number 2, where you're working with the variances and stuff. Part E, it's the last one we haven't talked about. Just simply use the jack.after.boot function to create the default diagnostic plot with respect to T, and comment on the sensitivity of the Bootstrap calculations for T using this plot. I just stuck there at that at the end because I wanted you to get some experience with this demo plot. That's all. It kind of doesn't necessarily fit into the rest of the stuff that you're doing.
So the boot.res that we use should be which one we've done 7 months?
There should be one boot.res that you are using with this as your number of resamples and this is your sequence.
Yeah, because your T is the same. Okay.
Okay. Okay, so now you have enough to do to finish this project. Now, also for this particular example in the book, they produce some additional plots. I don't really want to get them into too much detail, but just talk about them a little bit. This kind of corresponds a little bit to what I was discussing earlier with respect to regression analysis, and this gives you motivation for why they decided to do these plots. So first of all, what they decided to do was plot log of L2 and log of V1 on the same plot. And what I have here are the actual observation numbers instead of plotting symbols. You can see where number 2 falls. Remember, that was the one that kind of stuck out on our previous plot. And we have a regression line here with and without observation 2. And you can see that doesn't really have much of an effect. And you wouldn't expect that based upon where 2 is located from your Stat 870 kind of course. Real briefly, how did I construct this plot? I won't go through all the details. I just want to mention to you. Obviously, I used the plot function to get the scattering of the points. But note that I say type equal n here. Does anyone know what type equal n means? I don't think we've done it in this class. I know some other of my classes I have before. So looking at the students who were in one of my previous classes. Type equal n means no. Means don't plot anything. So basically it just sets up your plot without any plotting points. The reason being is because I want to use the text function that allows me to plot actual text symbols. Labels equal 1 to n. That's how I got the actual points on there. It also allows me to get the different coloring of the points too. Then I can use the AB line function with the results from estimating the regression model to put those regression models on there. Now the second plot is now the residual for log of L2. In other words, this is what I was getting at before. Let's use L2 as a response variable, and these other variables that I don't really care about in this partial correlation, let's use those as predictor variables and get a residual for them all. Similarly, let's use B1 now as a response variable and use these same other two variables that I don't really care about as predictor variables, get a residual. So in essence, what I'm doing is I'm removing the effect of these other two variables so I can look at the relationship between L2 and B1. And this is what we get in a very similar kind of plot. Notice where observation number 2 falls. Now this is one of the areas that often you're studying, something like Professor would say, a leverage point that's going to affect the line, and we see that happening there. And we saw then the effect that it had in our bootstrap analysis then with respect to this partial correlation. It had an effect too. It changed what happens with or without that observation. And also then to emphasize the point here is, well, what happens if I did remove observation 2? I don't know if I've ever mentioned this in this class, but hopefully you've seen this elsewhere through our experience. If I were to put a -2 there for the row number, that says use the frets data without observation 2. So that's a quick, easy way to get that observation out. Use the boot function, and notice what my observed value for the partial correlation is without number 2, 0.33. Compare that to what it was before, 0.13. My estimated standard deviation for the statistic without observation 2 is 0.17, with 0.2261. So you can see the effect that observation number 2 has. So also think of it in terms of what would happen in a hypothesis test, or you can think again about in terms of confidence intervals, what this effect, this observation 2 has. So then the question comes now, what do we do? What do we do with observation number 2? Just kind of smile and say, it's there, and move on.
Depends who you talk to.
Yeah, it does actually. It depends on who you talk to. I mean, in this particular case, I don't really know enough about the data to make a judgment of, well, what's this observation 2? Think back to your regression analysis days when you had, let's say, the influential observation. What did you do? Well, one thing that you could do is just say, okay, this is influential. You just unfortunately have to live with it. Of course, in any kind of paper or analysis that you present, a report, you should mention that this happens. But there's not a good thing that you could do with it. Another thing that you could do, and you have to be very careful about this, is actually remove the observation from the data set. But if you do that, just realize that now you are, let's say, making your population of inference smaller. So hopefully, maybe with this observation 2, with this particular family, this observation 2 is representing, maybe you could, say something about them, some characteristic about them that made them unique. And then you could say, well, okay, I'm going to limit my population of inference for this particular problem to all people except for those who have this characteristic. You should never just simply blindly remove observations from a data set and think, okay, everything's okay still. Don't do that. I guarantee you some of my 70 students will do that for projects coming up, despite me telling them don't. I once had we're running out of time here, so I guess I don't mind talking about this, but I once had a student in a Stat 870, or actually a group of students in the Stat 870 class. They fit a regression model, and they found some influential observations. What did they do? They removed them from their data set, refit the model, and what do you know? There are some new influential observations. Refit the model, let's remove those observations, let's refit the model. And eventually they got tired of repeating this exercise and they just stopped. Well, that's not what you do. Anyway, so what else in this particular section? This next stuff that I'm going to talk about, well, we can do a plot of B negative J minus B versus empirical influence values as well. This gets a little bit complicated, and it's going to take more than the 5 minutes that we have left. Students often have a hard time, at least at first, understanding what's going on here. So I want to skip over that and hopefully do that next time. What I will mention is that there is a nice recent paper on Bootstrap Diagnostics that was in 2006 Canadian Journal of Statistics. There's other Bootstrap Diagnostics that you can do as well. We talk about them there, in addition to the plot like we just saw. So, are there any questions? Okay, so next time what we'll do is we'll finish up Chapter 3 real quick, and then we'll go into Chapter 4, hypothesis testing.